All right. So last time, what we talked about was the critical temperature and critical pressure, and reduced temperature and reduced pressure, and using the generalized compressibility chart. That was our pretty much goal last time. We did a question on it. Today we're moving on to the internal energy, enthalpy, and specific heats of ideal gases. So there's a couple things I want you to take away from this. There's not a whole lot of like questions that you will ever get asked about this specific chapter, but there is something very important about this chapter, and it has to do with evaluating these two using with when you have an ideal gas. So we're going to go ahead and look through this. So it says, for a gas obeying the ideal gas model, specific internal energy depends on only temperature. Hence, the specific heat, CV, defined by equation 3a, is also a function of temperature alone. That is right here. So essentially what it's saying is that CV, so specific heat, in regards to only temperature, with respect to temperature, is equal to du dt. So essentially, the change in internal energy is only a function of the change in temperature, is what it's saying. And then we move on. So that's like the main thing we wanted to show. And so, let me see if I can move down here. And then the next thing I wanted to show is that the change in enthalpy, so the change in specific enthalpy, which is H, right, is the exact same thing. Because if you remember, H is just equal to U plus PV, and U is internal energy. So it follows that if U is reflective of only temperature, then H would be too. And so that says the same thing, is that H is also specifically only a function of temperature when you are working in an ideal gas model. Okay? And so why I wanted to say that, why this, I guess, is relevant, right, is the following. So we have a new table to go to. Table 822, the ideal gas properties of air. So let's go down there. I think I just missed it, actually. Yes, here it is. Oh, nope, that's not it. Oh, that was a little bit less. A couple more down. So, table A22, this is right here, is the ideal gas properties of air. So let me scoot out a bit. So what this table is essentially, come on, let's go back. What this table is essentially, if you have a question that is asking for, that has something in air. So for example, if it says 1 kilogram of air contained at this pressure, this temperature, something like that, right? This is where you have to go. And this could also work in other questions, right? Where you have like a heat exchanger with water coming in at these is exchanging heat with air coming in at these temperatures, right? So you have to go for here for the air values. So ideal gas properties of air. And how this table works is the following. So a lot of people draw a line down the middle here because it doesn't work like a lot of other tables. These are two separate sections. So for example, for temperatures 200 to 450, these are the values read across, right? It restarts over here. It goes down and then it comes back up and starts again at new temperature. So 450 to 740, right? So a lot of people draw a line down the middle. I'll leave that to you. And then on the next page, it continues for even higher temperatures. So 750 to 1280 and 1300 to 2250. And this is all in Kelvin, by the way. So Kelvin is where we're at. So, really quickly, so what some of these values are. So enthalpy is right here. Internal energy is right here. And these are, I think they're called absolute entropies or something like that. But don't worry about these yet. And don't worry about these yet either. We'll get to those very shortly. But for now, I just want you to be able to identify that on this table, if I were to tell you air is coming in at 350 degrees Kelvin, or if I gave it to you in Celsius, you would convert it to Kelvin, and you would come here. So 350. And these two are your internal energy and your enthalpy. So enthalpy being 350 internal energy being 250. Does that make sense? So this is, like I said, a new table that if you are ever asked about air, this is where you will go. Alright. Hopefully that makes sense. But we'll stay there for now. A lot of this stuff isn't all that... this stuff's not really that useful. I don't remember ever using something like this. But this right here is probably something to note. So K is equal to the specific heat, so CP over CV. And this was an equation that was listed beforehand in a previous section, but to reiterate it now, is that this is the specific heat ratio. So it's the specific heat I think it's CP is when it's pressure, so so specific heat with regards to pressure and specific heat with regards to volume. This is where we're at. It's these two. And these are both found in the tables, right? And right here, they're these two equations tell you how to find each of CP and CV. So K minus 1, and you get K from doing this, right? You can find things if you need to, but I don't remember ever having to do it. So I'll let you know if you do, though. So this stuff we've never had to use, so I'm going to go ahead and skip it. Alright, so I think this is where we have to keep going for now. So let me see if there's anything here that I need to find. No, essentially this right here is just telling you about tables A22, which is the air one that I we just looked at a minute ago. So don't worry too much about that. This right here just tells you that those values were put in a table, and that's the table we just looked at. So real fast, we're going to do a very simple question, but only this time, as you guys can see, we have air here, right? 2 pounds of air. So real fast, we're going to get a Paint 3D up, and we're going to go ahead and this won't take very long because this question is very, very short. So should be very, very quick. So, whatever, canvas, text. All right, so I got my text tool. So it says, a piston cylinder assembly contains 2 pounds of air at a temperature of 540 Rankine and a pressure of 1 atmosphere. So this is 14.7 psi. 1 atmosphere, something like that, right? The air is compressed to a state where the temperature is 840 degrees Rankine and the pressure is 6 atmospheres. During the compression, there is a heat transfer from the air to the surroundings equaling 20 BTUs. Using the ideal gas model for air, determine the work during the process. Okay, so we've been given a couple of things there, right? And like I said, this is how we should approach basically every question. So you just read it and kind of write down what you were given. So what were we given? Well, we were given the mass of air, right? So M air is equal to 2 pounds, right? That's one thing we've been given. The next one, we were given the first temperature, right? So it says air it was 2 pounds and it was at a temperature of 540. So this was before compression. So you should write T1 is equal to 540 Rankine. And really quickly, if this was given in Fahrenheit, you'd have to change it to Rankine because air works in absolute. So you have to change it to Rankine. So that's what we've been given so far. And we were also given a pressure, P1, of 1 atm, which is 14.7 psi, right? Okay, so these are the things we've been given, and there's a couple other things as well that we'll get to in just a second. So, one other thing we've been given is that we were given that it was compressed, right? So we know that the pressure had to have increased, and we also know that the temperature had to increase, right? These are two things, right? So we were given temperature 2 is equal to 840 Rankine, right? And then we were also given pressure 2 is equal to 6 atmospheres, I'm pretty sure is what it said. 6 atmospheres, so 6 ATM, which is just 6 times our first one, right? So we have our pressure has increased by a factor of 6, and our temperatures went up to 840. And then it says that heat transfer during compression, there is a heat transfer from the air to the surroundings. So can anybody tell me what that means? What does that actually mean for us? Anybody? Correct. So essentially what Tanner has said here is that this right here is the air. Our air is contained within this boundary right here. And it says that the air is transferring, so essentially from the air to the surroundings. So essentially there's some heat going out, right? So it's we're losing some heat. So, and it's 20 BTUs, so I'm going to go ahead and write that. So let's do Q is equal to negative 20 BTUs, right? So that's what we have so far. This is our knowns for the question. Now I got to get this back up. So knowns for the question are the following. Now we have to do what we normally do, right? Is that we have to find some things that we know about each state, correct? So let's move down here. So let's do step 1, or state 1 rather. So state 1, what can we find about this? So we know the pressure, right? And we know a temperature. So with what I told you just a minute ago, that air only relies on temperature to determine its enthalpy and internal energy values. So with that being said, do we have enough information here to determine the internal energy and the enthalpy? We do. And the reason why we do is because we have a temperature, right? Temperature is, that's enough. That's enough for us. So what we have to do is we go to table A22, and we find U is equal to, so we're already at table A22, except it has to be A22E because we are in English unit, so off we go. Because we were in Rankine, so I have to go all the way down to A22E, which I think is a little further from here. Oh my god. A lot of fluids. Alright, here we are. Almost there. So, A22E. So, what we do is we go down the table, and we find 540, which is our first state. So, 540, and you grab, which value do we want to grab here, by the way? So, remember, what kind of system is this? Let's go back here. What kind of value what do we want to grab here? Do we want to grab H, or do you want to grab U? Which one? So let me ask another question. Is mass flowing out of this boundary? Like, for example, as we compress this, is there any of this air leaving? Michael, I can't hear you. Yeah, for some reason I don't hear you. But there is no mass leaving, right? It's a closed system. And what did I say for closed systems? We should use internal energy, right? So U is what we should use for closed systems. So, since this is a closed system, we will use U here. And so, let's go back to the table here and let's grab the U value. So 540, and it's 92.04, so right here. And this is in BTUs per pound. So 92.04. 92.04 BTUs per pound, right? So that's state 1. We have found that pretty straightforward. Now we have to go to state 2. Because remember, since this is air, we don't need anything else, right? Our goal is to find just the internal energy or the enthalpy for these problems. And since we don't need anything else, like pressure or anything, we can move on, right? So then let's go to state 2. So state 2, we have 840 Rankine, right? So 840 Rankine, pretty straightforward. Since we have 840, we just go right to the table and figure out what 840 is. So you go down the list, right across to 840, and you grab that value right there, which is 143.98. So let me go ahead and grab that. So U2 is equal to 143.98 BT per pound, right? And this one over here should be U1. I've made a little bit of an error there. There, U1. So U1 is right there, U2 right there. So we have both U1 and U2. We also have a mass, right, which was given. So what we are here to find is our final step is that we are trying to find, so let me see, let me go ahead and write solution here. Our goal is to find work, right? What was the work of the system? And really quickly, as an aside, what type of work, should this be positive or negative? Think about it very closely. Waiting for some other answers here, and we'll... So Tanner and Michael are correct. And the reason why they're correct is that we are going to have to put in... So think about it this way. So Joseph, think about it this way, is that if this air was pushing the cylinder back, this is work that we haven't had to do, right? So think about the power stroke in a car. The power stroke in a car, the reason how it works is that essentially you compress it, so you have to input some work to compress it and get it, nice and small volume, high pressure, and then you ignite it. And when you ignite it, it fires down and shoots the piston down to the bottom dead center. And that distance that you shoot it down is all that power essentially. And so you get power going down to the shaft. And so this right here though is more like a compression stroke. So think about it this way: if you turned this, let me see if you can even do this. Let's see. Let's get real in depth here. So right here, this is basically this is a compression stroke in a car, because we're having to compress it, and so the piston is going to move up here. So essentially, we are having to put something in for that. It doesn't just do that on its own. We have to do it. But if we, say, ignited it up here, it would shoot the piston back down, right? So this is why this is a positive. This is a negative work. So let me get that back. Look how interactive this class is. So negative work, at least in my opinion. We'll see if that yeah, very lively. So let's see if it is though. I'm guessing it is though. So work is what we're trying to find. So work is what we're trying to find, and so we know a couple of equations, right? We know what Q minus W is equal to U2. So let's do U2 minus U1, right? We know this equation. I think everybody is pretty familiar with it. So this equation is known for us. But really quickly, there's a little bit of a snag with something else. It says determine the work in BTUs. which is a total energy unit. It is not energy per mass. So far, our energy units are in energy per mass, so they have to be changed. So that means there's something else I have to add here. So I have to do Q minus W is equal to M times U2 minus U1, right? So that's what I have to do. Although I think it's U1 minus U2. But once again, if you know what direction the work has to be, you can fix that at the end. But I'm fairly certain I have to go back. I have to change that. I'm pretty sure it should be the other way around. Like I said, if you're confident that you know if the work has to be positive or negative, it doesn't matter how you write it. But if you write it, I guess, the correct way, it'll come out, the units will come out, or the sign will come out right. Okay, so let's try that. So if that is our equation, now all we have to do is we have to fill in our problems, right? So we were given Q in the question to be minus 20 BTUs. So let's go ahead, minus 20 BTUs minus, let's go ahead and just make work as a variable, right? So W is a variable, and this is equal to, let's go ahead and drag this out. So this is 2 pounds times U1, which was 92.04 BTUs per pound, minus 143.98 BT per pound, right? So this is where we're at so far. So when you multiply in the pounds here, you can go ahead and just brush this. If you multiply in the pounds cancel here, and you're left with BTUs, right? And I will go ahead and pull up the handy dandy calculator. So we have 2 times the quantity of 92.04 minus 143.98. And so that is, so that right there should be that, and it's 2 times that. So it's 103.88. Okay, I think that makes sense. So let's make another text box down here. A little bit more summarization. So minus 20 BTUs minus W is equal to negative 103.88 BTUs, right? And so now we just have to do a little bit more work here by moving over 20, right? So if you add 20 to this, so let me go ahead and do that. So add 20. Let me see. So then we have negative work is equal to, and this should be what, 83? 83, negative 83, sorry. 0.88. Hopefully I'm correct about that. Yep, 83.88. So actually I think it should have been U2 minus U1, as a matter of fact. Because if you take the negative sign of that, you'll get a positive work here. So I had it right the first time, I think. But we'll see what the answer says. So let me see. See if I even did any of this right. That'd be awkward. So minus 20. Where did we do this? So Q. So they moved over Q. Oh, okay. Now I see it. So about the Q. That doesn't. Wait a minute. So the work is done on the system. That makes sense. But something here isn't quite right. Let me go back. I think I messed up the sign here. So if you move over Q here, I think I'm.
System gains internal energy,
Yeah,
from state 1 to state 2, right?
yes,
So that delta U, U2 minus U1 should be positive.
yep,
Yeah.
yeah. I realized. So I had it right the first time. No, because there are some questions where you don't have to. You do it the opposite way, and it's always flipped me up. But this is the problem: is that if you do it, sometimes if you have to do it the other way, like if you have to add something to it, it'll mess it up. And so yeah, that makes sense. So I had to write so it should have been a positive value of 80, or it should have been added this to it, so it should have been 123, right? So essentially, if we break this down a little more, I'll just flip this around. So it should have been 103.88 plus 20 is equal to negative work, is what it should have been, right? And so what that means is that negative works, or so work is equal to negative 123.88 BTUs is what it should have been equal to. Because if you change the sign, if you multiply by negative 1 on both sides, you get work is equal to negative 123, which is what it is. So, yeah, I should have had it that way, but whatever. So, that right there is the extent. So, I'm sure everyone in here is probably like, man, I like air a lot more. We don't have to use any of this. There's no saturate. So, really quickly, air does not have. Okay, let me rephrase. Air does not have like quality or saturated tables or superheated table, none of that. It just has this table. It is just this. So air is always easier to use, in my opinion. I think air questions are a lot easier. The problem is, though, is that as you have to try and find entropy, and you have to use these values, it gets a little more complicated for other questions. But it's even with this, I think air is just an easier thing to work with in thermodynamics. But that was basically what I wanted to show you, was that that table exists, and that's the one that you should use for air to air questions, more or less. But one more thing before we go, because like I said, I said we wouldn't be here very long. So there might. Yes. So if the question says something like this, air follow this, or it's like air follows or there usually is the bottom of it. It usually says something like, assume ideal gas, right, or something like that, or it says air operating at an ideal, or air is an ideal gas in this system at something, right? So in the question, it generally says it. But right here, for example, it says using the ideal gas model for air, determine the work, right? So there's always a hint. There's always something that tells you to use the ideal gas model. But just to be honest, basically every air question you'll ever do is going to be treated as ideal gas, unless you have to do those critical temperatures and critical pressures from the previous question. Then you're trying to determine if it's ideal. But for this right here, if it's ever a process, it's generally speaking just always going to be an ideal gas. Yeah. So it's nothing. Air is generally easier to work with. But there's one more thing I did want to say before we go, is that, I mentioned something last class about specific heats, and sometimes you have to do an average specific heat value for two things. To get an average value. So this is something that they do here. And so I wanted to show you that really fast. So right here. So when they did this question like us. So you remember that question we did the other day with the metal bar and the water or whatever it was? This is a very similar question. And they're trying to find an equilibrium pressure and an equilibrium temperature, I'm pretty sure. Or no, the heat transfer. So what you have to do is that you have to find an average specific heat value at two different temperatures. So right here they did CV as an average of 0.745 between 300 and 350 K. So at some points, if you have two temperatures and you have to use a specific heat value, it's better to take an average, such as this. And so if there's ever a question, or if there's ever something on an exam, generally speaking, I will say use an average specific heat value between these two temperatures. And then that is what I mean, okay? Just so no one is confused, that's what I mean. I want you to don't just take it at one temperature and say that that's good for all the temperatures that thing is going to have, right? That's not very smart, is to go let's say, for example, air is going from 300 to 500 Kelvin, and you just select the specific heat at 300 and go, yep, that's good. That's not right, right? You guys can probably figure it out. That's not right. You haven't really well defined how much energy it's picking up as you go up to 500, right? But if you select a specific heat, let's say at 400, so in between 300 and 500, it would better represent it. So that's what I'm essentially asking, is that if I ask you to use a average specific heat, that is what I mean. I mean to grab one in between two temperature ranges. Is that all good? Does everybody understand that? Okay, so basically this chapter is done. So really fast before you guys go, I'm going to go ahead and actually, never mind. We'll keep it going. So essentially, this chapter is done. We were supposed to do 313 and 314 today, and I think that's what we just did. So 313 and 314 were just done. And the last one is 315. 315 is basically a day where he would generally use a program. He would like show you EES on the screen. I do not have access to EES. At least I think that's what 315 is. I'll go look actually. Oh, it's polytropic process relations. Okay, with air. Yeah, we might spend a very short. This might be another short class on Friday, because you don't see a whole lot of this either. So this, remember we did this at the beginning of the class, right? You remember this, 1 minus n thing right here. But I have never seen him, and this is a fact. I've never seen him give a question with a polytropic process of air. But it's not much different than using the one from water that we did earlier, right? It's not much different. But that is basically the end of the chapter. So on Friday, it'll probably be another short day. And then what we'll do is next Monday, we are going to review on Monday. And then you will take your exam Wednesday. So real quick, I'm going to go ahead and shut this off.